Good morning. Hi, everyone. Welcome to the Yale Innovation Summit and the Roberts Innovation Showcase. I'm Claudia Reuter, and I have the privilege of working with the Roberts Innovation Fund's teams every year. And I'm delighted to introduce Dean Brock, who can tell you a little bit more.
Great. Welcome, everyone. We are now in our fourth cycle of awardees for the Roberts Innovation Fund. It's kind of amazing. Each year gets a little more exciting, a little more diverse, a little more robust. Since 2022, we've helped over 30 startups get out of Yale laboratories for engineering. This is kind of a new era, and we're just excited to see it grow into its next phase. In the next 5-year cycle, which we're happy to re-up and re-announce going forward. So what we're going to do today is we're going to have presentations from our most recent 10 awardees in this cycle. We've gone from just being really focused on things like software and AI to a much broader range of technical areas coming out of engineering. It's remained an engineering-focused fund, and the only requirement is that one member of the team be either a primary or secondary faculty member in engineering. So that's allowed us to really connect with a lot of different areas of the university and to see a really broad range of what Yale has to offer, make it out of the lab and into the marketplace. All right, so enough from me. I'm happy to introduce Allison Malloy from Connecticut Innovations. She's the managing director who will be running the show today. Thanks, Allison.
Thank you. Hi, everyone. I'm Allison Malloy. I've had the pleasure of getting to introduce the presenters over the last couple of years, and it's always really exciting to hear what folks are working on. So I really just get to come up and say the name of the company, but I get excited. So the first presentation is going to be by Claudia Che with Neuraleaf. Welcome.
Good morning, everyone. I'm Claudia Che, and I'm an assistant professor in the Electrical Engineering Department here at Yale University. And today I want to show you how we are changing the way epilepsy is treated using Neuraleaf, a lifting neuromodulation platform for epilepsy treatment. But every time I present a new idea or a new project, I always like to start with the most important question, which is, why are we doing this? And the answer is that more than 50 million people right now live with epilepsy. And despite all the available medication, 35% of them are experiencing drug resistance. So now imagine if a seizure, epileptic seizure, could actually be stopped before they even happen, using bio-inspired and fully conformable electronics that is capable of restoring brain function in real time, so naturally that the brain wouldn't even perceive them. But first, let's give a look at how epilepsy is treated today. So oral medication are the standard first line of care, but the problem is that they act systemically, not locally. So they're not targeted exactly where the epileptic seizure starts. And as a result, 1/3 of patients become drug resistant. When drugs fail, patients move to implanted devices, but the problem is that today's implanted devices are quite rigid and bulky. So for this reason, this accelerates device failure and long-term biocompatibility, meaning that the patients must undergo another invasive surgery after a few years. Our solution is a smart and soft implant that can deliver therapy locally, so exactly where the epileptic seizure begins, avoiding the spreading of it in the brain. And instead of electrical stimulation, which can introduce some side effects because you can tickle different areas of the brain, our device would deliver a molecule which is naturally produced by the brain. And the device would detect in real time the seizure and release the drug in real time. And because it's fully soft and conformable, this would improve the long-term usage and improve biocompatibility. So here is how the device works. So we have a fully flexible, implantable neural interface, which is multimodal. So the way it works is that it can continuously monitor the neural activity, identify the pattern that lead to an epileptic seizure, and then trigger the delivery of the therapeutic drugs. This implanted device would communicate with outside through the skin wirelessly, using a patch that is placed on the skin with a system that is called ionic communication, that leverages the presence of ions that everyone naturally has in the body to both power the device and transmit the data. But of course, what I'm proposing here is not science fiction. We made some steady progress towards the development of this bioelectronic device. So we started by developing the soft neural interface to see if we can physically integrate with the brain. Then we developed conformable electronic circuits that can continuously monitor the activity, analyze the data, and identify this epileptic pattern. And thanks to this work, I was named as one of the 35 innovators under 35 by the MIT Technology Reviews. And a few months later, in July 2025, I joined Yale as an assistant professor where I launched the Brain-Body Bioelectronics Lab. And now we integrated this fully flexible system with this flexible wireless communication that uses the ion. So I just want to underline the fact here that we are not using any rigid component at all, no batteries, no external cables, nothing. And now we tested this implantable device in animal models. So here is why we fundamentally differ from existing solutions. So what is missing from today's devices is something that brings all of these capabilities together. So the reason why Neuralif is different from the others because it can uniquely bring together localized drug delivery, real-time seizure intervention, battery-free design, and fully soft design. And by defining a new category of smart soft implantable neuromodulation system, Neuralif would enter a global market of around 750 million, with North American representing the 44% of them. So our device would have this start of around 66 million. And while we are personally very attached to the problem of epilepsy, this device can be used also for other type of diseases, can target different type of organs, and can deliver other type of drugs. So ideally like a bigger market opportunity. And of course, we were very happy to be selected among the Robert Innovation Fund's awardee, because through their help, we were able to, bring this working device into like a translational platform. But of course, this type of translation is only possible with the right people. So this is the Yale team behind Neuralif, and thank you everyone for your attention.
Oh my gosh, that's wonderful. Claudia, 35 under 35. That's so impressive. We're so lucky to have you here at Yale. I love this event because I feel like by the end of all these presentations, I just leave the room feeling so much smarter, just being around such great people. And I did want to just quickly say, I know that Claudia referenced that I'm with Connecticut Innovations, but we love to watch all of the companies that are going to be spinning out from Yale because we love to invest in early stage startups. So Connecticut Innovations, we're the venture capital arm for the state of Connecticut, and we deploy about $50 million each and every single year into startups. So if there's folks in the room that are looking for money, come find me over the next 2 days and I'll hook you up with the right people. So moving on for our second presentation, which is going to be by Catherine Miller Jensen and Quay, if Quay is here. It's engineering macrophages for next generation immune cell therapies. So come on down. Here we go.
Okay, wonderful. Thanks, everyone. So I'm Catherine Miller-Jensen. I'm a professor in biomedical engineering, and I'm here with my colleague and collaborator, Haoyuan Cui, who's in immunobiology and also BME. And we're here to tell you about our vision for engineering a new immune cell therapy. So there's a large class of diseases that remain incurable despite our medical advances. And these can generally be characterized by persistent disruption of homeostasis. So you can think about things like chronic non-healing wounds or neurodegeneration. And by some estimates, this is actually more than 40% of all diseases, and it's a largely growing class. So I like to think of this as an analogy, right? So I'm a homeowner, you have a house. If your body or your house is functioning healthy, then maybe one thing goes wrong. A window breaks, the plumbing goes, and you call in someone to fix it, and everything goes back to normal. But if you let that house deteriorate over time, you have a pathological state of the house. You need a general contractor to come in and fix that, okay? These diseases are like that, and what they require is a long-term regenerative therapy. So our vision is that engineered macrophages are uniquely positioned to potentially reverse this tissue disruption and restore homeostasis. So the reason is that macrophages are innate immune cells, and they are already first responders in our tissues. They're guardians of our tissue health. They already exist in most of the tissues in your body, and they perform restorative functions. And most importantly, they're central coordinators, so they can actually coordinate the actions of other cell types. So this is in contrast to T cells, which are also extremely powerful immune cells, but they are more specialized for single targets, right? So this is why they've been deployed very successfully against diseases like cancer and potentially autoimmunity, but they aren't as well suited for this kind of coordinated approach that we think that macrophages could fulfill. So, of course, there are some pretty serious bottlenecks to engineering macrophages, which is why we're here. Engineered macrophages currently do not survive for long periods of time in the body, and obviously that's a critical component of any cell therapy. And moreover, they do not home to and persist to the specific tissues where we need them. So that's another thing that we need to figure out. But the thing is, our macrophages naturally do that in our bodies, and so we think that we can harness this potential.
And so to overcome these bottlenecks, we propose to build a toolbox of genes and signals that when genetically engineered into macrophages will allow them to durably persist in the body and go into specific tissues that we'd like them to do. And in order to develop this toolbox, we will test hundreds of candidate genes and signals, drawing upon the regulators that macrophages naturally use to control their persistence inside the body. We will engineer them as a pool into macrophages, transfer these engineered macrophages into mice, and read out their persistence and tissue entry abilities in a single experiment. And our approach fundamentally differs from existing cell therapy efforts, and though there are existing efforts to engineer macrophages for cancer therapy and other diseases, none of these are able to overcome these persistence and tissue entry bottlenecks that we plan to solve. And our toolbox, if successful, will unlock multiple downstream opportunities. We can license this macrophage engineering toolbox to existing macrophage engineering companies, but we could also empower new therapies that we will plan to develop at Yale to target diseases that don't have any good treatments, including pulmonary fibrosis, cardiac fibrosis, and the healing of chronic wounds. And this technology, we envision, could complement CAR T cells and engineered T cell therapies to increase the reach of cell therapy and broaden its impact against a wider range of diseases. And we plan to build this engineering toolbox within this 12 months of Pilots Roberts funding, aiming to complete a pilot screen in 3 months, to finish the full screen to identify targets in 9 months and validate these targets to establish our toolbox in 12 months. And the funds from the Roberts Innovation Fund will allow us to co-advise research personnel, laboratory supplies, and also fund animal studies.
Yeah, so here's our team. Once again, we can't do it alone. So we also have Claire, a graduate student, and Gabby, a postdoc. And we're really excited about this opportunity to start this collaboration and synergize our expertise for this new cell therapy. Thank you.
Thank you so much. Okay, this is on? Maybe, maybe not. Okay, so our next person is Chen Zhang, who's going to be talking about continuous ultra-high temperature plasma synthesis of extreme particles.
Good morning, everyone. Okay, I think. Good morning, everyone. So today I would like to introduce our work on continuous ultra-high temperature plasma synthesis of extreme powder. So I'm Qian, postdoc from electrical computer engineering. So I team with my PI, Dr. Liang Binghu, who is traveling right now. So I'm presenting on behalf of him. So extreme materials, so as it's called, is usually used under extreme environment. For example, the aerospace engineering and the nuclear energy. So, for example, these materials are used in making rocket nozzles or like plasma-facing material in the plasma nuclear reactors. So usually these materials are like, of very high melting point and of very high hardness. So they are very hard to make and they are very expensive. And then so usually these parts, that's when we use them in nuclear reactor or in rocket nozzle, require precise and delicate manufacturing process. In that case, so usually people use additive manufacturing to make these customized parts. So powder as a feedstock is very essential in additive manufacturing. So this is why we want to make high quality powder. So these are the, however, there are challenges in commercialized powder making process. So these are the gas atomized powder that I show here from commercialized gas atomization process. So usually these powders are not spherical, and also they have a lot of satellite particles. And then so commercialized gas atomization or water atomization usually just limit the temperature below 2000 K, which means like they are very hard to make extreme materials because usually these materials are with melting point above 2500 K. So, and also there are multiple steps, like usually require days to prepare a batch of these powders. So what we do, so why we want high quality powder? So usually we want this powder be very spherical because when we like spray this powder to make powder bed, we want these particles flow like beans, not just like flour when we cook in kitchen. Because usually when you make a cake, this flour will like form this powder cake. And if you don't sieve the flour, they will just get stuck. But we want this powder be flow like beans on the powder bed, and they don't clog the nozzle during the 3D printing process. And also we want, when they form the powder bed, we want them be packed as dense as possible. So when we print, so the final parts will not have internal pores, and this deficiency will actually cost like all these manufacturers a lot of money because of all these defects in the final product. So take home message here: we want particles of high sphericity and also dense internal structure. So how we solve this problem? So we invent a ultra high temperature plasma platform that can reach temperature up to 8000 K. So what I show here is the 8000 K plasma created in our lab. So these high temperature plasma allow us to make spherical powders and also with ultra high melting points. So all these powders I show here are above their melting points are above 205,000 K. And then, 2,500 K. And then so we can make them just within seconds. And then so and also when we maintain this 8,000 K, we only like consume 1.5 kilowatts, which is an extremely energy efficient process. And we can see like very obvious improvement compared to other commercialized powder. And right now in our lab, we are able to start to scale up the process. So for this technology, we published this paper in Nature by the end of 2023, and we filed the patent. And we found a company called US Plasma, and we were being also supported by APA-E program using this plasma technology to make high-value carbon allotubes. And also last year, we are R&D 100 awards. So this year, so at the beginning of this year, thank you, Claudia and Grace, and we're very glad that we are being funded by Roberts Innovation Fund to continue our research on this like perfect powder making. And then so compared to our competitors in the field, so from this cross section, so basically the cross section is just like we cut a summer watermelon and see how the powder looks like inside. So we see this from this cross section view, we can see our powder like compared to other commercialized powder, so they are more intact in they are more intact inside, and also the cross section also show our powder are more spherical compared to our competitors. So we believe, so there are huge markets, so estimately 7 to 9 billion out there. And we believe this market is still growing. Actually, because recently the government started to launch the space program, and also we have Genesis mission to start to strengthen the fundamental manufacturing in this country. So this makes additive manufacturing and all these advanced like technology be very important. And we believe our powder, perfect powder, can play a role inside. So this is our milestones with Robert. So this summer, so I'm working on making a scale-up invention, scale-up powder feeder to make at least 1 kilogram of powder. And then this is the team. So on our team, we have experienced researchers, and also we have very strong support from UConn, and also like from industry. So thank you.
Thank you so much. Does this work, or did we put it back off again? On, off. Oh, it says
On, up above. There we go. Okay. This is wonderful. We're scaring people. People are leaving. People are coming. I also said I want to be invited back when we brainstorm on really short names for the companies, right? It takes me like 10 minutes to introduce them. Okay, so we're moving on. This is wonderful. Our next person is Jean Granjou, and we're going to be talking about design of intrinsically porous polymer-based membranes for crude oil refining.
Hi everyone, my name is Zhongren. I'm a PhD student in Professor Minjiang Zheng's group. And our project for the Robot Innovation Fund is design of intrinsically porous polymer-based membranes for crude oil refining. So crude oil, or usually referred to as petroleum, is one of the most important energy sources in the world. Every day, around 10 million barrels of crude oil are separated into different valuable products, and they can be used for like transportation or different industrial applications. So conventionally, the crude oil is primarily separated by the thermal distillation. So in the distillation, different products will be produced based on their boiling point or the molecular weight. So usually from top to the bottom of the distillation column, we'll first get some light oil like gases, naphthas, kerosene, and end up with some heavy oil like asphaltes. Although thermal distillation could afford efficient separation of the crude oil, it's quite energy intensive. According to the literature, around 50% of the energy consumed in the industrial area are caused by the separation process. And in the separation process, around 50% of the energy comes from the thermal distillation. And people found that by applying membrane-based separation technology, we can save more than 90% of the energy caused by the thermal distillation. Therefore, in order to decrease the energy consumption in the crude oil separation, we have developed organic solvent nanofiltration technology, OSN. So during the OSN, some feed solution, or in our case, the crude oil, will interact with the membranes. And based on the membranes, crude oil's heaviest or their molecular weight, we can concentrate the heavy oil in the retentate and allow the light oil to pass through the membrane and concentrate into the permeate. Therefore, we can achieve the separation of the crude oil with much lower energy consumption compared to the thermal distillation. So here comes our membrane synthesis and fabrication. Here we developed a novel polycondensation to synthesize the so-called polyamino triazo polymer as our membrane material. So this kind of polymer consists of the contorted and rigid polymer chain that can form the intrinsic pore. And this kind of intrinsic pore can help to precisely separate crude oil into different valuable products. And after the synthesis, we try to fabricate a kind of thin film composite membrane by combining our polyamino triazo nanofilm with some commercial spore layer. So this kind of nanofilm can help to maximize the permeance of the target oil product or increase the production rate of the target oil. And this picture is our nanofilm. Since it's too thin, so the thickness is around 20 nanometers, therefore it's almost invisible. So after the synthesis and fabrication, here comes the preliminary test. Here we utilize a kind of benchmark test to preliminarily evaluate the membrane performance in crude oil separation. Here we want to separate the TIPB, a kind of heavy oil, from the toluene, a kind of light oil. And we have two metrics to evaluate the membrane performance. The first is separation factor that reflects the membrane's ability to separate light oil and heavy oil. And also we have permeance to reflect the production rate of the light oil. This diagram summarizes the performance from different literature. Those gray dots are from the reported membranes, and those colorful dots are our membranes. As you can see, our membrane almost beat all of the reported data and exhibit both the high separation factor as well as the high permeance or the production rate of the light oil. Therefore, our membranes overcome the trade-off between the selectivity and permeance, which is not achieved by the previous work. And here comes the real crude oil separation test. Here we apply a kind of cascade membrane-based fractionation of the crude oil to simulate the practical crude oil separation in the industry. In the first stage, we're going to use the PA2C3 thin membrane to remove those ultra-heavy residual from the crude oil while remain the mixture of some light oil like the kerosene and naphtha. And in the second stage, we're going to use PA2C3 to precisely separate two different valuable light oil, kerosene and naphtha. So the left figure is the first stage separation. Based on the mass spectrum, we can see that most of the heavy fraction or the ultra-heavy residue are removed in the first stage. And you can also see the change of the color or the appearance of the oil. So initially, as one feed or the crude oil is a kind of dark and viscous wax. But after the first stage separation, it becomes the transparent and yellow liquid. And in order to compare our membrane performance to the thermal distillation, we also measure the boiling point of our samples. The gray curve is the crude oil. As you can see, it contains a lot of heavy oil with high boiling point. But after two stages separation, we can achieve 91% purity of the naphtha and 82% purity of the kerosene. So the naphtha, the kerosene we get is a kind of a yellow liquid, and the lightest product, naphtha, is completely colorless and transparent liquid. And based on the calculation, we found that by adding one more stage of the thermal distillation, the crude oil separation based on membrane, we can achieve up to 98% of the purity for both the naphtha and kerosene. And that means we can get a comparable performance to the thermal distillation, but with 90% less energy consumption. So when it comes to the market opportunity, the current market size for our OSM membranes is around 0.35 billion project for the 2033. But for the whole crude oil separation market, it's around 13 billion based on their projection. And some commercial suppliers, they can provide some membranes for like usual organic solvent nanofiltration, but none of the commercial products are suitable for the crude oil separation. And some petroleum companies like ExxonMobil or Shell have already reached out us and express their interest in our material and provide some crude oil samples for our test. So for the future plan, we're going to recruit a postdoc researcher to further push the upper bound of the trade-off and set up some equipment to enable the large-scale membrane fabrication. And we'll also seek some opportunity in industry to conduct pilot-scale crude oil separation test. And last is our team. We are like a big interdisciplinary team, containing multiple like synthetic chemists, chemical engineers, material scientists, and environmental engineers. That's it. Thank you for listening.
Thank you. Great job. Okay. Our next person coming up is going to be Crystal Pollitt, who's going to be talking about ExpoSeq Environmental Sequencing for Personalized Health Insights.
Hi, thank you very much. Well, good morning, everyone. I'm Crystal Pollard. I'm an associate professor at Yale, and I have a cross appointment between chemical and environmental engineering as well as in public health. And I work at the intersection of these disciplines to understand how the environment is shaping health. And today I'm presenting ExpoSeq, an environmental sequencing platform that we built for breast cancer survivorship. So in the United States, there are 4 million women that have completed breast cancer treatment. But even after they've completed the treatment, the questions linger. Will it come back? And what can I do? Their oncologists are telling them to watch their diet, to exercise, to manage their stress. The chemicals in their daily environment, especially endocrine disrupting chemicals, hundreds of them, are known to influence their breast cancer risk. Oh, dear. But it's not included within any of their treatment plans right now. And we know that all of these chemicals are critical in terms of how breast cancer evolves, especially during 4 critical windows of hormonal periods within puberty, prenatal, pregnancy, and menopause. And these have all shaped the pregnancy research markets as well as wellness markets as now. But this 5th window of survivorship is now emerging as one that doesn't have a dedicated prevention strategy. So how are we measuring what a woman survivor is being exposed to? Chemicals from our daily environment are constantly entering the air, even air within this room right now. Sources like furniture, textiles, personal care products all contain additives. And these additives are not chemically bound to these products, which means they're able to migrate into the air and they're continuously released. So the air acts as this integrative sink from an incredibly diverse range of sources. And with our past studies, we've been able to then follow the air that people are exposed to and see how dynamic they are in terms and shaped by their personal activities. So I'm showing the exposures here for 2 endocrine disrupting chemicals. An antimicrobial found in many personal care products, where we looked at it within 80 individuals, and we can see that over the course of a 5-month period where there was repeated assessment, we see that there's consistent exposures because you have consistent use of these products. We can then also look at a pest control product for mosquito-based dichlorobos. We can see enhanced levels within the summer periods and declining seasonally as our patterns change. And so how we're able to then address this, our solution starts with looking at a silicone film that we can embed within a wristband that an individual then wears throughout their life. So flame retardants from a woman's furniture, plasticizers from her water bottle, fragrances from preservatives, and personal care products all migrate into the air around her. The silicone then acts as a molecular sponge that then passively collects all these chemicals as she moves around her daily activities. And this is the principle that ExpoSeq is founded around. So this is the fresh air wristband that's at the heart of the ExpoSeq platform. A woman will wear it for 7 days, and then we use a high-resolution mass spectrometry approach that's then able to then sequence her exposures. And then we can estimate this for about 500 compounds from a single wristband. But we don't just hand her a list of chemicals. We then triangulate this with the sources around her and then be able to then provide her with actionable insight that she can then use. ExpoSeq is not just a research platform. It's built on a decade worth of validation within my research group at Yale, also high impact publications and 2 patents. We've sequenced the exposures globally with over 30 partners in 25 countries, and this also includes partners that are actively engaged in breast cancer survivor research. There is currently no other wearable technology that captures the chemical signatures from everyday life. Our competitors have 20 to 30 chemicals at best that they can detect, or a single pollutant. We're able to look at over 500 different chemicals, and this can also then include the potential to include pathogens, metals, as well as microplastics at a price point that we're able to then have repeat use. And we are the only product that's able to then personalize this into personalized treatment and action. The public consciousness of environmental health has never been higher. And breast cancer survivorship is growing at an incredibly large market, with over 400 women that have completed treatment and 300,000 that are completing treatment every year. It's one of the fastest growing patient populations in oncology right now. These are also not passive patients. These survivors are among the most health conscious consumers that are investing in nutritional counseling as well as active lifestyle management. And we are looking to then provide them with the environmental insights that currently they're not able to understand. Roberts Funding is giving us a clear 12-month path. We're building currently personal exposure assessment kits. This summer, we're deploying it together with the Silent Spring Institute across the US with a crowdsourcing campaign. And then we're currently also building an app to then personalize environmental report back with action plans for health optimization. We're working with a great team. I bring the engineering and exposure science background. We're working with David Gaudry on the digital platform and also Sharon bringing this commercialization expertise to take it to market. So thank you very much.
Thank you. Our next presenter is Anthony Fung, who got the memo on a short name, who's going to be talking about GlycoDX.
Hi, good morning, everybody. My name is Tony Fung. I'm a postdoc fellow in Professor Rong Fan's group in the BME department, and I'm serving as the interim CTO of the company, GlycoDX, which provides researchers and clinicians with new spatial glycomics tools for precision health. Sorry. Okay, so nearly a century ago, the United States declared war on cancer by establishing the NCI, yet it remains not just a persistent but growing problem. A significant population of cancer patients are actually misdiagnosed, and it's generally well accepted that early and accurate detection is critical to patient outcomes. Now, to that end, many companies have developed tools along this biological assembly line, from genomics and epigenomics to transcriptomics and even proteomics. But today, GlycoDX is shedding new light on the spatial metabolomics landscape through our spatial glycomics platforms. So post-translational modifications are essentially sugars that decorate this polypeptide chain, and they directly affect how a protein folds. And when AlphaFold, the pioneers at AlphaFold won the Nobel Prize, tackling this post-translational modification question was too ambitious. What we've observed is that these changes in the glycosylation of these proteins, or these glycan motifs, actually precede a lot of the transcriptional changes in disease states, offering potential early biomarkers for many of these diseases that are very difficult to diagnose. Additionally, these glycan profiles are generally well preserved even in archival FFPE tissue. And now this affords training on rich archival samples. So together, the probes that we're developing are poised to deliver clear and intuitive signals to delineate your next biomedical question where the existing probes might struggle a bit. There are hundreds of millions of archival FFPE tissue blocks in existence, and fun fact, Yale pathology has samples that are over 200 years old. So in the age of AI, who knows what kind of rare insights we might uncover using this technology. Our surveys with pathologists have indicated that our imaging platform can deliver very clear and intuitive pathological insights with a lot of granularity, less noise, and more consistency, as shown in this human lymph node sample with lymphoma. And you heard that right. This is one of the first simultaneous ultra-high-plex antibody and lectin platforms. And using the same exact sample, we can analyze disease states, protein phenotypes, and glycan motifs all at the same time. Now, existing spatial glycomics platforms typically handle just a handful of glycans. But GlycoDX offers non-destructive, AI-powered, deep interrogation into diseases non-destructively at just a fraction of the cost, because compared to antibody production, lectins are dirt cheap. Now, this technology is very flexible and we can apply it to many diseases, but by assuming just a small, modest 3 to 5% of the spatial probes and services market, we're already at a sum of tens of millions. Now, this is excluding the value of one of the first and largest spatial metabolomics disease databases. And we're grateful for the Roberts Innovation Fund, and with the generous budget afforded by Roberts, we're going to continue to hone the probe development and expand it to virtually every disease we can, including hopefully the expansion into liquid biopsies to afford population-level screening. What you see here are these are actual biopsy cores that we stain the sugars on instead of staining like the proteins. So beautiful things tend to happen at the intersection of Yale Engineering, Yale Medicine, and Yale Ventures. And this is really exemplified by our leaders in men's business acumen. And it's with those steady hands that they'll usher us into a new era of glyco-precision health. Thank you.
Thank you. We have a few more wonderful presentations that are just moving right along. So Chen Liu and Pranay Mundra will be talking about Silhouette DB, differentiality, private graph database. Thank you.
Hi, everybody. My name is Chen Liu, and I'm an assistant professor in the Yale Computer Science Department.
Hi, everyone. I'm Pranay Mundra. I'm a PhD candidate in Yale Computer Science.
And we're so excited today to tell you about our product, Silhouette DB, which is the first differentially private graph database. So you've all been told a lie about data privacy. That is, if we delete your name from a publicly released database, then your data is safe. So this is a lie. That is, if I delete your name from a publicly released health data set or your perhaps embarrassing viewer habits, then your data is safe. But this is a lie. If I know who you talk to, who you pay, and who you work with, then I don't need your name. I know what your data is because your connections are your fingerprint. So this is the main problem. In fact, this touches almost all industries that deal with private user data. So examples of such industries are finance, healthcare, the government, and almost every other social platform nowadays that you see in existence. So here are some examples of use cases that deal with graph analytics. So examples are patient referral networks, supply chains, social networks, etc. So all of these companies use private user data and graph analytics. And because of this, despite the wealth of data that can be used for research, innovation, or additional product development, all of this data is currently locked up in individual company silos because they're too dangerous to use in public. So we now introduce our solution to solving this problem. So we want to bring to product our innovation, Silhouette DB, which is the first high-performance differentially private graph database. So let me explain to you what these terms mean. So differential privacy is one of the strongest guarantees of data privacy. It is a mathematically founded guarantee that your data will be kept private. And my expertise is in high-performance computing. And being a high-performant graph database means that it will be scalable to billions or trillions of edges or nodes.
So let me describe what our database does at a very high level. So our database will provide all the same functionality as all of the existing databases. It will offer common graph analytics such as subgraph count, centrality, community detection, but with the caveat of differential privacy built in. The way we do it is by carefully and automatically tuning the amount of noise we add based on each individual graph input and the graph property. This noise is calibrated such that it hides sensitive graph attributes, and it's not too much that it'll disturb the useful graph property signals. So our output will simultaneously be insightful but safe. And we'll offer, in addition, real-time data auditing, so we are compliant out of the box. This is how SilverDB would work. This is for organizations that have highly siloed data that need cross-border analytics without compromising privacy. And SilverDB would allow you to collaborate on everything without sharing anything. This is what a world with SilverDB would look like. Era of borderless medical research, transparency on social platforms, anonymization. From anonymization, you go to noise injection, and you can generate synthetic data for your external partners. Large companies like Google and Apple currently have their own dedicated teams, but for smaller organizations, research organizations, this is hard. So this is where SilverDB would work. And this is what the traction has been. Our product began as an open source GitHub repo, which we released in April 2025. We then had a publication in a first-ranked database conference, VLDB, in July. Then in August, we were contacted by a stealth startup looking for exactly this product. And then finally, in February, we got the Yale's Robert Innovation Award. And this is what the current differentiation is. Currently, there are tabular databases that exist and that offer differential privacy. There are graph databases that exist that offer no privacy guarantees. However, no database exists that offer both graphs as well as differential privacy, and this is where SilverDB comes in. This is the market opportunity that we're looking at. Our current SOM is around $120 million, and the near-term market revenue is $6 billion.
We have a wealth of experience, as well as affiliations that will help our product become a success. And we're very thankful to the Yale Ventures team, as well as the Roberts Innovation Fund for their support.
Thank you so much. After Jack, we have two more. So Jack Harris will be talking about geometric amplification of laser light. Come on down. I'm like, which way am I looking?
Okay, so although it is built using very sophisticated technology, at the end of the day, the internet is semaphore. By that, I mean that every single piece of information, every bit of data, is sent as an individual pulse of light that has to travel all the way from its source to its destination. As a result, lost light means lost data. So how far can a pulse of light go before it's lost in practice? This is the telecom backbone of the United States, spanning 5,000 kilometers end to end. A pulse of laser light can travel down modern optical telecom fibers 50 kilometers. That doesn't get you from here to New York City. That doesn't get you from here to Stanford. It might get you to Bridgeport. Okay, so the internet is not just semaphore, it is semaphore on a foggy day. You cannot see very far. The reason that the internet still works is that there are amplifiers that boost these signals over and over again as they travel from place to place. Here's a representation of the scale of demand for these amplifiers, about 1 million to be installed just in the past year. 1 million is a lot of amplifiers, and they work. That's the good news. The bad news is that they are built using technology that hasn't changed since the mid-1980s. That's our opportunity. So if you think about what features you would like any amplifier to have, here's a list of some of the things that might crop up first. You have two choices at present. There are two forms of technology. The first are the EDFAs, they're shown here, and they offer you the items on the left. The other option that you have are the SOAs, shown on the right. They offer you the list on the right. You have to pick one or the other in every single application. Okay. So we regard this as a weak link. Nobody wants to give up half of these desiderata just to have the other half. In my group in the last few years, we have developed a fundamentally new form of wave amplification. This isn't a new way to realize some existing idea. This is a form of amplification that is new at its basic mathematical description. It can be applied to any form of wave signal. In our lab, we have applied it to mechanical vibrations, not because we want to make more vibrations in the world, but just to show that it really works and that we really understand it. We are very keen on applying this amplifier to the problem I just described to you of telecom laser light. We can tell you right off the bat that it offers the following performance features. The ones indicated by the locks are ones that we're still studying the fundamental performance of. So just to give you a sense, this is Yale Ventures' estimates of the size of the market for telecom optical fibers up top. Down below is shown sort of a food chain, if you will. These are examples of very incremental developments in laser amplifier technology shown on the right that get snapped up quickly by the bigger players. So at present, we have our invention, we have the IP secured through a patent application, we have our proof of concept via the amplification of mechanical vibrations. We would like in the next year to realize this to amplify laser light using chip-based wafer-scale foundry. Support from the Roberts Innovation is allowing us to spend this year developing a more compelling prototype, which is to say an amplifier of laser light that is not on chip, but is built using discrete consumer off-the-shelf components to give us a very compelling prototype of laser amplification. So hopefully the next step involves this being translated to real industrial deployment. Our team is myself, research scientist Yogesh Patel, who's here, graduate student Tony Montalvo, who's here also, and thanks very much to Roberts, and thanks to you for listening.